This is LeetCode number 23, merge k sorted lists. For this question, we are given an array of k linked lists, and each linked list is sorted in ascending order. And we need to merge all the linked lists into one sorted linked list and return it. And in the example they gave, we are given three linked lists: 1, 4, 5, 1, 3, 4, 2, 6. And our final output should be 1, 1, 2, 3, 4, 4, 5, 6. The constraints for this problem are k is equal to lists.length. That means the number of lists here is equal to k. And k is between 0 and 10 to the 4th. So k is between 0 and 10,000. Lists I.length is between 0 and 500. So each of these lists has between 0 and 500 elements, and lists ij is between negative 10,000 and 10,000. So each of these elements is between 10,000 and negative 10,000. Lists I is sorted in ascending order. So each of these lists is sorted in ascending order from lowest to highest. And the sum of lists I.length will not exceed 10 to the 4th. The wording is a little weird, but what it is saying is that the number of elements will not exceed 10,000. So if you add up the length of this, which is 3, and you add up the length of this, which is also 3, and you add the list of this, right, which is 2, then it'll be less than 10,000. Next, let's take a look at an inefficient solution and see how we can get an efficient solution by making a few tweaks to it. For this solution, we're going to compare every k nodes, or the head of every linked list, and get the node with the smallest value. And then we're going to extend the final sorted linked list with the selected nodes. So let's see what they mean by that. So first, they're going to compare the heads of every node. So 1, 3, 2. And 1 is the smallest, so 1 is going to be in the result. Okay, so next we're going to have 2, 3, and 2, and 2 is the smallest, so we're going to move 2 down here in the result. Next is 2, 3, 4, so 2 has the smallest value, so we're going to move 2 down here. And 3, 3, 4, so 3 has the smallest value, but this list comes first, so this 3 is going to be moved down here. Next, 3, 4, 4, so 3 has the smallest value, this 3 is going to be moved down here. And 4, 4, 6. So this 4 here is going to be moved to the result here, and etc., until they arrive at the final answer. So this solution, the time complexity is O of k times n, where k is the number of linked lists. That is because almost every selection of node and final linked list costs O of k, or k minus 1 times comparison, and there are n nodes in the final linked list. So what that is saying is there are n nodes in the final answer, and to find, for example, that this node belongs in this spot, it took k comparisons. So let's see what that means here visually. To find this node here, we had to compare 2, 3, and 2. So we had to iterate through 2, 3, and 2. So the number of lists is k, and this is actually equal to k. So we found that the minimum was 2 by iterating through 3 elements, or k elements. So that's what they mean by this. So to get that 2, we had to make k comparisons, and we had to do that n times. Hence, the time complexity for this solution is O of k times n. So next, let's talk about the space complexity. What they say is that the space complexity is O of n to create a new linked list, and O of 1 to if we apply the in-place method. So what that means is there are 2 ways to go about creating this final list here. So the first way is if we use, let me erase all this. So the first way is, suppose we have a 1 here, and that 1 is we're going to consider this to be the same one in the result. What we can do is we can create a copy of this node here. So create a copy of it, and then this will be the one we see in the result. And so obviously, if you create a copy of all the nodes here to create this, then the space complexity will be O of n if there are n nodes. What we can also do is the in-place method they're talking about. Let's say this is a 3 and this is a 2. What we can do is we can, instead of creating a copy of this 1 here, we can reuse this node here. And same thing for this 2. So this 1 is this 1, this 2 is this 2. So how would we connect this 1 to this 2 to match the result? Well, 1 is right now connected to 3. So what we're going to do is we're going to break this connection and we're going to connect 1 to 2 instead. And then we're going to do that. We're going to, restring and mess around with all these connections here and rewire the nodes until we finally arrive at this solution. And by doing that the second way, we get an O of 1 space complexity. So how do we go about optimizing this solution? One of the things we can do is look at where we're doing repeated work and making that more efficient. For example, to find the lowest element among this 1, 3, and 2, we're iterating through 1, 3, and 2. And we're saying this one is the minimum. So we take it out of here, we stick it down here in the result. And this took O of k time. So next we need to iterate through this 2 here. So same 3 as before, and the same 2 as before. So 2, 3, and 2. And these two are the same. And we say, okay, 2 is the minimum. So 2 is in the result. And this, again, took O of k time. And the third time around, we iterate through this 4, the same 3 again, and the same 2 again. So 4, 3, same 2. And we find that 2 is the minimum, so we take it out. So we take it out here, and we stick it down here. And this, again, took O of k time. So visually, you can see here, this is where we're doing repeated work. How would we make this more efficient? The first time we're saying 1, 3, 2, we're iterating through everything. The second time we're saying, we're trying to find the minimum, so we're iterating through 2, 3, 2. And the third time we're iterating through 2, 3, 2. So this here is where the repeated work is. We're iterating through these two elements over and over again. Instead of iterating through each time, why don't we do some extra work this first time around so we have to do less work later on? Instead of just saying 1 is the minimum among 1, 3, and 2, we sort it. We say 1 is less than or equal to 2, which is less than or equal to 3. And we take out the minimum here, which is 1. We stick that goes here. And then we keep this information so that the next time we encounter this 2, we only have to find where it is relative to this sorted list of elements instead of iterating through all of these. So where does 2 belong relative to this? Well, it belongs right here. And we can find that in log k time. Right? It's essentially a binary search because this here is sorted, so we only have to find where this 2 belongs inside of a sorted list. So we take out this 2 here, and we stick it in the result here. And so next, we have this 4. All we have to do is say, where does this 4 belong relative to this 2 is less than or equal to 3? Well, it belongs at the end here, right? And this information here is reused. And so we take out this 2. And now we can reuse this for the next iteration. So that 2 was taken out and put here. The data structure we can use to do this is called a min heap. Min heap. It's a min heap because we want the lowest element first and the highest at the very end. So min heap or a priority queue. And that will allow us to reduce this O of k to O of log k. And therefore our solution goes from O of kn to O of log k times n. Next, let's start coding our solution. So first, let's start off with some edge cases. Our input is an array of list nodes. So each list node is going to be the head of a linked list. So for example, if our input is just this one linked list, then it will look like this, where 1 refers to this. So what if lists is null, or lists is an empty list, or lists just has one linked list in there? If lists is null, or lists.length 0, then we can return null because there's no output. If lists.length equals 1, so if they give us just one linked list, then we can just return the linked list because this list is guaranteed to be sorted already. And next, let's initialize some variables that we're going to be needing for our solution. So the first two variables I'm going to initialize are called dummy, or two list nodes called dummy and current. So what these two nodes are going to do is, suppose I have, well, my solution initially has nothing in it, and current is pointing to dummy, and let's say my solution has a 1. So now my current is pointing to the 1, and my solution, I need to add a 2. So now current is pointing to 2. And I'm going to add a 3. So now current is going to point to 3. And this here is my solution. And I need to return this node here. So I would just simply return dummy dot next. So that's what these two variables are for. Next, I'm going to initialize a priority queue. And this is going to be a priority queue that holds list nodes. And the order is going to be based on the values of the nodes. So so what this is saying is, for this priority queue, if I have two nodes, L1 and L2, compare them based on their value. And if L1 is lower than L2, then L1 will be ordered before L2 in the priority queue. Next, let's put the heads of all the linked lists inside of our min heap. So what that means is, let's start off with, let's use the example that they gave us in the prompts. 1, 4, 5, 1, 3, 4, and 2, 6. We want to compare these three using a priority queue. So first we're going to put all of these nodes inside of a priority queue. Side priority queue. For int I equals 0, I is less than list.length, I++. Our input initially starts out looking something like this, right? 1, 1, 2. But they can also, throw us a curveball, right? It could be a null in here as well. So we need to account for that. So we say if lists I is not null, then we're going to do min heap.add lists I. Next, let's construct our output. So we have already added all the heads of every linked list onto our heap. So it looks like this. And what we need to do is remove the minimum element and add it to our output. What that looks like is list node min equals min heap dot remove. And we need to replace this one that we just removed with its next node. So we remove this one, so we need to add 4 onto the min heap. What that is min heap dot add min dot next. And keep in mind this node could have been the last node in its respective linked list. So we need to do a null check in order to avoid putting nulls onto our min heap and getting null pointer exceptions. Next, we need to add this 1 that we just removed to our output list. So right now our output list looks like this. The dummy is pointing to nothing and current is pointing to dummy. We need to add this 1. And then we need to increment this current pointer to point to this. Current.next equals min. That adds this 1 to current.next, and current equals current.next. That moves the current pointer from here to here. And we need to do this until we run out of elements. How do we know if we run out of elements? Our min heap, this, will tell us when we run out of elements to compare. While min heap is not empty, so we're going to rinse and repeat until we run out of elements. Is min heap empty right now? No. Then we remove the minimum, which is 1. Replace it with the next element, 3. Current.next equals min, so 1. Current equals current.next. So is min heap empty? No. So we remove the minimum, which is 2. We replace it with its next element, so 6. Current.next equals 2, and current equals current.next. Next, is min heap empty? No. So remove the minimum element. Replace it with the next element. So the next element is 4. Current.next equals min. Current equals current.next. Is our min heap empty? No. Remove the minimum, and that's this 4 here. Replace it with the next element. Our min heap looks like this. Let me erase all this. 4 current equals current.next. The next, is min heap empty? No, so we remove the minimum, which is 4. And that's this 4 here. And replace it with the next element. Well, the next element is null, so we don't put anything onto the min heap. We say current.next is min. Current equals current.next. So next, is min heap empty? No. We remove the minimum, 5. Replace it with its next. Well, the next is null, so we don't add anything onto the min heap. Current.next equals 5. Current equals current dot next. So is our min heap empty? No. So we remove the minimum. And does 6 have any more? Is there any element after 6? No. We don't add anything onto the heap. Dot next equals 6. And current equals current dot next. So now we need to return this, the head of this linked list. And to do that is return dummy dot next. Next, let's run our code. Okay, great, it worked. So our time complexity is going to be O of n log k, where n is the number of elements across all the linked lists, and k is the number of linked lists, because we are only ever adding or removing from a min heap of size k, and we're going to do this n times. And our space complexity is going to be O of 1 because we are reusing the same nodes from our input in our output. That's going to be it for this video. Thank you for watching. Hope you enjoyed it. Please like, comment, subscribe.